We'll have a demonstration of our tool SWAT, which contains our own worst-case response time analysis techniques. Our tool is developed by the researchers of Co-Design and Parallel Processing Laboratory in Seoul National University in Korea. SWAT stands for Seoul National University Worst-Case Response Time Analysis Tools. Our tool supports various features of real-time applications and the systems, and provide a way to model the systems with the user-friendly graphical interface. SWAT includes various worst-case response time analysis so that you can choose the proper technique fitting the purpose. We provide our own 4 techniques in SWAT. STBA finds an upper bound of the worst-case response time by performing scheduling of task instances. Similarly, HPA generates an upper bound, but it is based on the response time analysis technique. ILP-based analysis finds exact worst-case response time using integer linear programming. Worst scenario generator provides a lot of real worst cases to show the worst-case behavior. This is our system model. Application is represented as a set of task graphs. We support period, input jitter, minimum distance, execution time variation, and dynamic offset. The processing elements can have fixed priority preemptive policy or fixed priority non-preemptive policy. From now on, I'll demonstrate the way to model the target applications and the system with our tool. It is very easy to model the system with our tool. Add processing elements on the editor plane. You can choose the modeling elements on the left side of editor. Then select each processing element and set scheduling policy on the properties window. Now select the task and draw a rectangle on the processing element. Then the task is made and is mapped to that PE. In this example, I made 2 tasks on each PE. After that, set execution time variation, priority, and the name on the properties window. BCT means the best case execution time, and WCT means the worst case execution time. You can define the data dependency between tasks with dependency edge. Select the predecessor first and select the successor second. Now group the tasks that is invoked with same period. Add task group on the editor and multi-select the tasks and assign those tasks to task group. Tasks assigned to the same task group has same color so that we can easily recognize the same task group. Period, jitter, and minimum distance parameters is also defined on the properties window. After system is modeled, worst-case response time of the applications can be analyzed with our methods. You can run each analysis with the buttons listed on the top of the editor. Complete worst-case response time for the applications are shown on the console window. ILP-based analysis shows the exact worst-case response time results. You can see the worst-case scenario founded by ILP-based analysis with the Gantt viewer. You can see each task's start time and end time and preemption behavior on the Gantt chart. Test case generator generates near worst case scenarios by collecting converged population in the progress of generic algorithm. And you can see those scenarios also with the Gantt viewer. Our tool provides additionally end-to-end delay analysis. This is the real automotive examples. Select two task group, which is the begin task group and end task group you want to analyze. When end-to-end task groups are defined, our worst-case response time analysis methods additionally finds worst-case end-to-end delay and path. The end-to-end path is displayed with red thin edges. You can also see the end-to-end delay with the Gantt viewer. This is another example that models risk management systems runs on the automotive ECU. Main algorithm consists of several tasks that has dependencies, and it runs with the information from sensors. Sensor sends data periodically along the canvas, and integrated ECU runs risk management algorithm and sends the result to the actuator along the bus. As same as previous example, we can analyze the worst-case response time of each task graph, as well as the end-to-end delay from sensor to actuator. In our demonstration booth, you can experience the usefulness of SWAT, and we will show you the performance of our own techniques by comparison with other well-known analyses.